All right, so we have already started the Simplex method, and we're basically going to finish it today. So things might get a little bit fast in the beginning, so it's very easy to get lost. That's why I sent you the email to go over and recap before coming to this lecture. That's what I want to do in the first 5 minutes. I want to sort of recap what we did last time and then start moving on from that point onwards, all right? Okay, so what did we do in terms of the Simplex method? So what did we learn 2 weeks from today? We learned about standard form, right? You remember? This was one of the things. So I'm going to talk about each one of them in detail, why we need it. We talked about the standard form linear programs. So we are going to restrict our attention to standard form linear programs. Why this is the case? It's very important. Okay, second, what else did we learn about? You remember? We said that, okay, in the graphical solution, everything is perfect. We go from one corner point to the other one. This would be the case with the Simplex method, but we need an algebraic characterization of these corner points, and that brought us to basic, I'm going to put in parentheses because they might not be feasible, basic solutions. Okay, that was another concept we talked about, remember? Good. Okay, what else? What else did we talk about? We talked about neighborhood. Okay, so in the graphical solution, everything is nice. You see these corner points. You see whether they are neighbors, they're close to each other or not. But the Simplex algorithm is going to start with one of them, go to a closed one in a greedy fashion while improving the objective function. So we need to define this closeness. We need to define what does it mean for two corner point solutions to be neighbors. Algebraically again, all right? And what else? This was perhaps the last one we left out with. It was, what was it? It was canonical form representation. Okay, we're gonna keep all of this information in a neat representation, which we call canonical form, so that at every iteration of the Simplex method, we know where we are, what is the current solution, we know where to go next in order to improve, if any steps are to be taken, and so on. So this canonical form representation is very, very important. But all of this, basically, it's not new to you. You have already covered most of it in 225, so I'm going to try and sort of set it in that setting, what you'll know from 225, whether we can use it directly in our Simplex method. All right, any questions so far? Yes. I don't hear you. Okay, maybe if I come down, would it be better? For me at least, but for you? I can see you now. Yes, now I can hear you too. I will remind you all of them, but anything before that? Okay, all right, so let's get going. So the first one is perhaps the easiest one. What is our LP? Our LP is either a min or a max. These are the structures we bother solving, right? Is it okay if I stand here? All right, okay, we have equalities, and we have non-negativity of the variables. Standard form says that all of our constraints should be equalities. Standard form says that, so we should have equalities. Oops, I didn't mean that. We should have all equalities here. That's one of the requirements of the standard form. What is another requirement? We should have the B vector all non-negative, okay? What else was the requirement? We should have all our variables to be non-negative. And we can have either a mean or a max problem. So Simplex method is going to deal with structures like this and is going to find an answer, if there is, to a structure like this. There was one other thing we wanted. What was it? In the standard form requirement. So if I tell you that A is an M by N matrix, it's rectangular, it has more columns than the rows, we had another requirement. Okay, we had another requirement saying that rank of A equals M. In other words, it is full row rank. All right, so I can find as many linearly independent columns or rows as there are rows in my matrix. Okay, why did we need this requirement, do you think? Why? How does it help us? So think about your linear algebra background. All right? In your linear algebra, we just focused on the system of equations, right? This is 225. Ax equals to b. We didn't bother about the objective. We didn't bother whether the x vector is a non-negative vector. All we said was, does a system of equations have a solution? Okay? And if I give you, in that sense, Ax equals to b, where A is M by N, you know exactly when the system of equations have a solution. When is that? When you have your augmented matrix, you put the column, the right-hand side column B next to it. If the rank of that augmented matrix, how should it compare with rank of A? To have a solution? Come on, this is linear algebra. What does the system of equation ask me to do? Does there exist a set of values in the x vector such that when I multiply the columns of A with these weights, I will be able to represent the B vector, right? So is B in the column space of my columns defined by the A matrix? This is true if I have exactly equality over here, all right? And if my rank of A is equal to M, that's the maximum I can have, right? So whether you put another column in or not, you will have the exact same maximum rank number. So rank of A being equal to M guarantees that I have a solution to this system of equations. Does that make sense? This is again from 225. Okay, it's a system of equations that has a solution. I still have to worry about, even if Ax equals to B has a solution, I still have to worry about whether it's a non-negative set of weights in the solution, and moreover, in an LP, I have to worry about whether it's the minimization of an objective function, this vector that handles or not. All right, so I can deal with this. This was 225. Rank of A being equal to M guarantees that, but I need more. I need non-negativity. I need it to be the best one, optimizing some objective behind. Does it make sense? So far, so good? Okay, so getting to standard form was very easy. And we have an example here. Let me go through that. Okay, in this example on the left-hand side, we have an arbitrary LP. The LP has less than or equal to constraints, equality constraints, greater than or equal to constraints. It has some variables that fail non-negativity because they are non-positive, they're unrestricted. All of it we could change to the second LP in standard form by adding variables, if we like, to represent the difference of two non-negative variables as an unrestricted variable by changing less than or equal to into an equation and so on. So all of this was very clear as far as I can tell, right? All right, so getting to standard form is very easy. We also assume that I'm going to get rid of all of my redundancies, so I will have this full rank assumption on my A matrix, and all of this was without loss of generality. So I can always is get my LP ready for simplex to begin. This is without loss of generality. Getting to standard form is without loss of generality. You don't lose anything in the meantime, okay? All right, next thing. What was the next thing? The basic feasible solutions, the notion of basic feasible solutions. Now, why did we bother? Again, we have our graphical solution. That's feasible region. You know from the fundamental theorem, it's enough to just think about these corner points. So these corner points are actually the basic feasible solutions in the algebra terms. So corner points is something very easy. You can look and see whether it's a corner point or not. But if you have higher dimensions, what does it mean to be a corner point? So corner points are exactly our basic solutions of AX equals to B system. Okay? So the potential feasible solutions in my feasible region, the corner point solutions in my feasible region in higher dimensions are exactly the basic feasible solutions in algebraic terms. Okay, so what is a basic feasible solution then? Let's see. So what is a basic solution? I have my AX equals to B. I know that A is full rank. Okay. So what does it mean? I can find M columns very easily, which are linearly independent. So I can write my system A as B matrix and then N matrix, where the B is M by M, and the N is the remaining M by N minus M. Okay? I can always do this. Rank is full. I can always do this. I can always bring some M linearly independent columns to the beginning. So what I would require from B is that it is invertible. So all of this is without loss of generality. Okay? I shuffled my X vector in a similar manner so that the first M are exactly the columns corresponding to the B columns. So I have my XB corresponding to the B columns, the same partition. I have my XN corresponding to the remaining. And B and N have names as basic and non-basic. Okay, this partition is always possible. There are tons of many such partitions, actually. I'm going to ask you how many do we have in general. And I represented my system in a similar manner with this partition. Okay? Now, AX equals to B is the same as BXB with my partition. Take the B submatrix, multiply it with the coefficients and the X vector corresponding to these columns. So there are M such basic variables and N minus M non-basic variables, right? So my system, by the way, these are all in the notes. If you like, you can take notes, but you don't have to. They are already in the slides. Just try to understand the basics of it. So BXB plus NXN equals to B is an equivalent form of my AX equals to B system, right? Okay, and then we said that our corner point solutions are going to be exactly the solutions in which I take such a B matrix out of my A, I do my partition, and I set my XN variables equal to 0. N minus M such non-basic variables, all of them are set equal to 0. Right? This is one of the infinitely many solutions, right? So I'm going to set it equal to 0. That brings my system to a smaller form. But now what is nice about the system is that it is in equality form. This is the one that you like, right? M is a square matrix. It's M by M. It is invertible. So that's the easiest one to find solutions for. You have a unique solution, XB equals to B inverse B, right? So what did we do? We took our A matrix, we divided it into two linearly independent columns in the beginning. This is always possible, and got to a unique solution defined by such columns which are linearly independent. Okay? Now that solution, okay, where should I go? Clear all, yes. Okay, that solution, xb equals to b inverse b, xn equals to 0. So as a vector, this is a basic solution. Right? This was attainable because my A matrix is full rank M. Such a solution is always attainable. Ax equals to b has actually infinitely many other solutions. This is just one of the solutions that we can get, and we can always get such a solution. Okay? But remember, it's not just Ax equals to b I want to deal with in LPs. I want to also have non-negativity, right? So these are my basic solutions. I know how to get. If it turns out that the unique part that you attain, the b inverse b, is a non-negative vector, this basic vector becomes a basic feasible solution. And these are the ones that we are basically interested in. Okay, not just any solution of the system of equations, because in an LP we also have non-negativity, so we would like to see basic solutions which are also non-negative in nature. Right? And if you remember, we had an example. Okay, let me go through that example. Okay, this was a system. The left-hand side has two variables, so we had the two variable case in order to pinpoint the correspondence between corner points and basic feasible solutions. I added slacks to convert the system of equations into standard form. It has two rows, 4 columns. It has two linearly independent columns, so this is a full satisfaction of my requirements. So I can talk about basic solutions and basic feasible solutions to the standard form system on the right? And we sort of enumerated all of them. This is the LP, the corner points in 2 dimensions of that left-hand side LP, and then we translated our system to standard form. That corresponds to an A matrix, which is 2 by 4. I have 4 columns. I know that 2 are linearly independent. I try all possibilities for choose 2 and see which ones result in basic feasible solutions. Not all of them resulted in basic feasible solutions, right? Not all 6 resulted in basic feasible solution. There was a one-to-one correspondence with the corner points of this 2 variable LP and our basic feasible solutions. Remember? Okay, so we tried all possible cases, choose the first 2 columns out of the A matrix. For example, I choose these are my columns. Oops. 1, 2, 3, 4. I can choose 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. These are all 6 possible choices of the V matrix that you bring to the front. Solve for uniquely, find your B inverse B, see whether it's non-negative. If it's so, it's a basic feasible solution. Okay, we had a bunch of them. Let me put, for example, the 5th one, in which you choose the 2nd and 4th columns as your basic columns. They're linearly independent. It results in a basic vector, but that unique basic vector has a non-negative component over here, which means that it's not a feasible basic solution, okay? It still corresponds to the intersection of a bunch of lines, so some corner point, but not in the feasible region, okay? And then we said that, okay, so we have 4, basically, and this is no coincidence because they're in one-to-one correspondence with my corner point solutions in the 2 variable LP. Okay, so finding basic feasible solution, at least theoretically, we know how to handle, okay? All right, still within LP, Simplex, we still have to decide where to start and how to move to the next one. That's another condition. So far, so good? Basic feasible solutions, clear? Okay, now, adjacency is another terminology that we talked about. So basically, I'm going to say that, okay, I will start with one of these corner points, let's say A. That's going to be my first step. And my improving direction, I think it was something like this, C vector. I will ask, or the Simplex method will ask, that it moves to a neighboring solution which has a better objective function value. So starting with 1, it could go to, for example, number 2 over here, then number 3, and declare this as the optimal one. Okay, so the Simplex method is still going to hop from one corner point to the other one. We now know what is exactly a corner point in terms of algebra. They are basic feasible solutions. So we just have to ask, how do I choose the next one to go? All right, so that brought us to the definition of neighboring solutions. Neighboring basic solutions. Okay, so what does it mean for two basic solutions to be neighbors? We have a partition in a basic solution. There are basic components, there are non-basic components, basic variables, non-basic variables. What's happening is that one of the basic variables leaves the basis and another one enters the basis. In other words, in two adjacent solutions, the roles of a single basic variable and a single non-basic variable are switched. Okay? I find out of the non-basic variables which are currently at 0 value, which one to go from 0 to something higher, because I need non-negativity throughout. And I find the best one in terms of my objective, and that eliminates one of the current basic variables. Okay? So if we go back to over here, if you like, clear. If we go back to over here, A and D are neighbors, right? If I look at the set of basic variables in D, they're x2 and x3. If I look at the set of basic variables in A, they're x3 and x4. So x3 is common in both of them. So in getting from A to D, I basically kick out x4, and I put x2. All right? So one variable leaves the basis, another one enters, and there is a switch, and I only consider one switch possibilities for neighborhood. So if you look at, for example, A and C, they're basic variables. X1 and X2 is the basic variable set for C, and X3 and X4 is for A. They don't coincide at all, right? I have m basic variables. I need m minus one of them common into adjacent solutions, okay? M was equal to 2 in our case, so m minus 1 equals to 1, but I need one common one in order for me to declare two basic feasible solutions as neighboring basic feasible solutions. Is neighborhood clear? So if you give me a starting basic feasible solution, I will look at my objective and decide which non-basic variable should go from 0 to higher, because it's going to improve my objective. But only one non-basic variable is going to enter at a time, and that's going to change my whole vector, and it's going to replace one of the basic variables, currently a basic solution. Sounds good so far? Okay, now the question, the fourth one, right? The canonical form representation. This is not new either. Actually, you know this much better than I do in terms of Gaussian elimination. Remember Gaussian elimination, linear algebra, pivoting, and so on. You did all of this in order to solve a system of equations, AX equals to B. maybe not knowingly, but you basically hunted for the basis component of your solutions, and then you represented all of your solutions in terms of these basic solutions. So nothing is new. So let me go back to my AX equals to B. Forget about non-negativity. That part you didn't know in 225, so I give you that. I have my A matrix, and I know that my A matrix can be divided into basic and non-basic columns, all right? What you basically did, actually, remember you shuffled columns around, you shuffled rows if you like, and you brought your matrices to a form in which there's identity in the beginning, right? If the rank is M, you have M by M identity matrix in the beginning. You did this through Gaussian elimination. Right? You did pivoting, you wanted all diagonal elements equal to 1. You zeroed out the remaining, you got to the identity matrix. And this is possible because it's basically equivalent to pre-multiplying your A matrix with B inverse from the pre-multiplying from before, right? So if I pre-multiply, so the steps of Gaussian elimination, row echelon form, and so on is all equivalent to pre-multiplying that matrix with B inverse, getting to identity in the beginning, and then what do you have under n columns? B inverse n, okay? This is exactly what you did in terms of Gaussian elimination. Well, you did a little bit more than that. You had B, you had N. You augmented it with the right-hand side B vector, right? And you did all of these changes to the same components in this augmented matrix, correct? So bringing it to identity, bringing it to identity means pre-multiplying everything with B inverse, so the N components are multiplied, and the right-hand side is also multiplied, okay? Now, the first I components are my first n variables, then the remaining n minus m, all right? And I have my right-hand side. The first variables I call my basic variables, the remaining non-basic variables, and I have my right-hand side vector. Okay, so I now have represented my set of solutions in terms of the spaces solutions. You have xb, right? So I times xb, b inverse n times xn equals to b inverse b. Now this system is exactly the same as ax equals to b after Gaussian elimination. You buy that? You changed nothing. You shuffled. You did row echelon form. You brought your first m columns into the identity columns. You did everything to the right-hand side matrix, and you brought your ax equals to b into this form. This is basically the canonical representation. Okay? Is that clear? Rana, was it? Okay. Is it clear? Yes. Why do we do that? Good question. Okay, that will come next. As soon as you buy this, all of you buys this, I will explain why we did this. Okay. Why Simplex method needs this. So in linear algebra, this, I don't know what representation you called it, normal representation or something. This has a name. So you have sort of the set of all feasible solutions at your hand. You can put down any values for the xn variables. You have xb variables uniquely solved once you have xn variables fixed, right? But we're going to say that our, I need clean pages. So we have xb plus ixb, b inverse n, xn equals to b. That's my new system after Gaussian elimination. I am going to set xn equals to 0 in the hunt for corner point solutions. So that brings me to xb equals to b inverse b system. Correct? And this is the basic solution, why it's coming from, and so on. It's nothing new. Everything you know already. It's just rewording and putting into sync with sort of the simplex method. Okay, so what does that tell me? That tells me exactly how the basic variables will change in terms of the non-basic variables, right? So right now I set xn equals to 0, but if I set the xn components to some values, 0, 5, whatever, I will still be able to solve for the basic variables uniquely. Okay? Now keep in mind of neighborhood definition. So right now, all of my xn variables are equal to 0. I'm asking, does there exist a better neighbor that will take me to a better objective function value? That better neighbor, I will be able to pinpoint through this canonical form representation. Okay? So if I know at every iteration, I should be able to see the whole picture. I should be able to see what is my current solution. This representation, definitely canonical form representation, gives me that. I have xb values equal to b inverse b. That's fine. I should also be able to pinpoint which one of the non-basic variables, if it moves up from 0 to something higher, if it enters the basis, it will be desirable in terms of my objective. That's also why we need the canonical form representation, but not just for ax equals to b. We now also have to bring in my objective into the picture, because everything the simplex method needs, it needs to find solutions, but also favoring more desirable ones in terms of the objective. Is it clear so far? Okay, so very long debrief of what we did last time. Okay, let me see. Number of basic feasible solutions is n choose m. We can enumerate all of them because our theorem, fundamental theorem, says that it's enough to choose any one of them as your optimal solution. If there exists an optimal solution, one of these basic feasible solutions will be optimal. So you have an algorithm, which is sort of a dummy brute force algorithm. Try all possibilities, look at their objectives, try the best one. This is too long, so we don't like this because the number of basic feasible solutions is too much, okay? So we don't like enumeration. Even with very small numbers, this enumeration could go very fast, very big, very fast. So we do it in a faster way, and that's simplex method. We talked about adjacency. Okay, adjacent basic feasible solutions, two basic feasible solutions. So what does it mean to be a basic feasible solution? I should have a partition of basic and non-basic. When I look at two neighbors, their basic ones, m minus one of them should be in common, all right? That's the definition of adjacency that we just seen. We looked at this example also. So the general description, I translate everything to the standard form. This is without loss of generality. Somehow I get an initial basic feasible solution. We're going to be cheating a little bit. It will be very obvious in the beginning, and then we'll talk about how to do that in general. And then as soon as I have a basic feasible solution, I will ask, can I improve it? Does there exist an exchange which will make my objective better? And as long as there are such exchanges, I will keep doing this exchange in favor of getting to a better corner point or basic feasible solution until I can find none, all right? And that's my stopping criteria. Okay, now the canonical form representation. And now the objective function also comes into the picture. So remember, we had an objective function, Cx. We're going to maximize it in the beginning. It doesn't matter whether we're doing maximization or minimization. So we have this LP at hand, maximize Cx, Ax equals to b, and x non-negative. Okay, I'm going to forget about this. At least I won't be writing it explicit at all times. I will always remember that all of my variables have to be non-negative in structure. And everything I do, these exchanges between basic and non-basic, I will have to maintain non-negativity. So I will forget about this. But as for the objective, I am going to call it Z. And I'm going to write my objective as sort of an equation, z minus cx equals to 0. And I will keep in mind that it was a maximization objective that I was trying to solve. This is changing nothing. This is just so that I can get to this canonical form so that I can pinpoint exactly what type of change will be better. And I will do this change, exert this change in a very simple tabular form representation. Okay? So you buy that this is without loss of generality. Okay, but I have to remember that I put my Cx values to the left-hand side. Okay, so for example, let us say that I had 9x1 plus 10x2 as my z values. If x1 goes up, I get better values. If x2 goes up, I get better values because of the positive coefficients. Now, in my row of 0 representation, I will have negative coefficients here, but I will remember that they're coming from the right-hand side, so still negative means good for a maximization. Okay, always keep this in mind. This is typically forgotten in the steps of the simplex method. Okay? All right, now let us consider this, again, simple LP. Two-variable case, of course, why bother, you might say, but everything we do in this two-variable case, you can extend it to any number of variables. So there will be LPs, and there are LPs, believe me, that you won't be able to solve using the graphical method, so we need simplex method, and there is no bypass of that. Okay, but as for the left-hand side LP, it's a two-variable case. You could solve it directly using the graphical method. We give you so that we can cheat and see the steps of the simplex method, what's happening when we translate everything to the standard form. So the right-hand side LP is a standard form LP, right? How did I get it? I added two slack variables. I enforced that those slack variables are all non-negative in nature, okay? Now, what is a basic solution to this system? If I look at my A matrix, what is my A matrix? That's my A matrix, right? Now, in the A matrix, I look for a set of columns which are linearly independent, right? And I get B inverse B as the right-hand side. Let us choose those columns as the slack variables. So in other words, my B is the identity matrix. So everything sort of comes out in neat form, simple form. B inverse is the same as the identity. What is B inverse B? My B matrix is the right-hand side, 6 and 8, so B inverse B is the same as B, which is 6 and 8. Okay? So if I start out with the initial basic feasible solution in which basic variables are S1 and S2, S1, S2, and non-basic variables are my original X1 and X2, right? It's a proper starting basic feasible solution, correct? In other words, what does it mean in terms of my, yes, what does it mean in terms of my graph? I am starting at the origin because these are my X1 and X2 values equals to 0, and I am having S1 and S2, the slack variables as my basic variables in the extended system in which I have 4 variables instead of 2. Does it make sense? So this was possible because I cheated and gave you a system in which my original LP had all less than or equal to constraints. The right-hand sides were non-negative. You added slacks, and now you can forget about the original variables or set them equal to 0, start with the origin, and have the slack variables as your basic variables, initial basic variables in the simplex algorithm, okay? This will always be possible if I have always less than or equal to constraints, but I won't, and we'll talk about what happens next. Sounds good? Okay, so now I have my basic variables. I'm at point A, and I also have to find out what is the z value currently at this solution, and whether I can improve it by going to neighbors or not. All right, that's the idea. Sounds good so far? Okay, so let us come to our canonical form representation where I put everything in terms of a tableau, and then we're going to simplify it. So I wrote my z on the left-hand side in row 0 format. So instead of x1 plus 3x2, I wrote it as z minus x1 minus 3x2 equals to 0. Nothing has changed. And I have my two equations as still here, right? This is my first and second equation. That hasn't changed either. And I wrote down my row 0, or objective function, as if it was a constraint itself. This is going to guide me what is the current objective function value, can it be improved or not. So it's part of my equation set if I consider it as z minus cx equals to 0. Sounds good? Okay, now what have I gained? Not much, it's the same idea, but now if you look, and what did we see? Say non-basic variables were x1 and x2, right? Which means their values are going to be fixed at 0. So if you fix them at 0, in other words, if you kill x1 and x2, you see in this canonical representation that the current objective function value is 0. And you have your first basic variable with value 6, your second basic variable with value 8. All right? In other words, you can pinpoint the solution right away as x1, x2, s1, s2. These are non-basic, and these are your basic variables 6 and 8. And you can also see that the objective function is equal to 0. All right, this is what the canonical form representation is helping us. Simply to tell us what is the current solution, what is the objective value of the current solution, and whether I can improve it or not. Okay? Now, one thing you noticed, each variable, each row has its own basic variable. I'm going to consider z also another basic variable. So the first row, row 0, has z as its basic variable. Second one has s1, and the third one has s2. Right? So this is my basic variable z, that's s1, this is s2. All right? Now, what have you noticed about the basic variables? They only appear in their respective rows and nowhere else. So if I look at under z, s1 and s2, what do I notice? I notice the columns of the identity matrix, right? So which means that I will see exactly the effect of any one of these non-basic variables in all these equations, okay? So you have only two non-basic variables in this case, but only one of them is going to be chosen to be incremented to some positive value. It's either going to be x1 or x2. Only one at a time. The other one will be fixed at 0. So you will be able to see the net effect directly in the objective function as well as in the constraints. And that's why we need the canonical form representation. Does it make sense? This is very, very crucial. And we're just shuffling the information, but it's going to help us dictate where should I go next. What is the current solution, and whether I should go to B or D from this point onwards. All right, I am currently at A, I know this. Should I go to B or should I go to D? Or maybe I should stay at A because that's the optimal solution, all right? All of this information you can get using the canonical form representation. Sounds good? Okay. All right, so let's see if I skipped anything. So basically, in the canonical form, I need one basic variable in each equation, 0 coefficients everywhere else. My basic variables are going to be s1 and s2 in this case, non-basic variables, x1 and x2, and I'm going to add my z as one of the basic variables as well. So in your A matrix, it's as if that you picked the S1 and S2 columns as your basis, but these are identities, so everything works out very easily as far as this basic feasible solution is concerned, right? Because B inverse B is the same as identity times B. Okay. And that's my current solution if I say that z is also a basic variable. Okay, so wrap up. Canonical representation. There's a basic variable, one for each constraint. This basic variable only appears in the equation in which it is basic. Z variable is special, chosen basic variable. It should appear in the objective function as the only single basic variable, and all of the remaining variables are non-basic. But if you sort of erase the non-basic variables from the picture because their values are equal to 0, you see that z value is something, the current basic variables have their certain values, and so on. The solution is obviously available. Okay, so that's what we have. Now, I am going to ask the question, am I optimal? Can I improve it? Okay, what is my option? I can only go to a neighbor, meaning that I could either choose the non-basic variable x1 or x2 and move it from 0 to something higher. Okay, the other non-basic variable, the non-chosen one, will stay at 0. Okay, so for this, you just simply look at the objective function. Remember, I had z equals to x1 plus 3x2. But in row 0 representation, z minus that equals to 0. So if you increment x1 by 1 unit, the objective function increases, right? If you increment x2 by 1 unit, the objective function increments further. So out of the two non-basic variables, which you have the option to increment or enter into the basis, remember, I will move to an adjacent one, meaning that one of the zeros will become positive. You will choose which one? x2 in a greedy fashion. This doesn't always guarantee that it results in the best solution, but you would choose x2 and sort of improve its objective function value. Make sense? So I am currently at this A point. That's my BFS corresponding to this point. And I chose x2, and I'm going to say, okay, how far should I increase x2 from 0 onwards? Per unit, you gain something in your objective function. You gain 3 units. So you would like to make x2 as high as possible. Okay, what is hindering you from making x2 1,000, for example? Can I make x2 1,000? No, why not? It's not, I will be leaving the feasible region. So x2, so I'm going to move along this line, right? Making x2 higher and higher. But of course, there will be a blockage coming from me because by making x2 higher, what am I changing? So x2 appears in this equation. If it becomes 1, s1 drops down from 6 to 5. If it becomes 2, s1 drops down from 6 to 4. Okay, so I am going to ask what is the highest possible? Why highest? Because per unit I gain 3 units in my objective function, which is to be maximized. So what is the highest possible without me leaving the feasible region? Making sure that any non-basic variable, if it enters, it's going to change all of the current basic variables. x2 is not going to change the x1 value. Why not? Because x1 I'm going to keep at non-basic and 0. I only choose one of the non-basic variables, and I chose out of x1 and x2 to enter because it had the highest potential of improvement. But only that one will become positive, the other one will stay at 0. So I will see what will happen when x2 increments to s1 and to s2. That's another reason for the canonical form representation. I will see the direct change in the current basic variables if I increment my x2. Sounds good? Okay, so let's take a break.